Hi everyone. In the previous classes, we have seen the concept of adders, which are meant for to perform addition of 2 bits, where we will use half adders. If we would like to perform addition of 3 bits, we are going to use full adder. If you would like to perform n bit number, n bit number, or we can call it as a binary number. We can call it as a binary number. We will use binary adders, right? There is a drawback that we observed in binary adders, so propagation delay is more. That's why we have seen the concept of carry look ahead adder. Okay, fine. So now let's see how to perform the subtraction also, right? So subtraction, right? So as the way we are having like half adder, full adder, binary adder, like carry look ahead adder. Here also we have first one is half subtractor, means it can able to subtract one bit from another bit. That's it. Meaning that if you are trying to subtract between two bits, I can call it as half subtractor. How mean the reason is it is trying to perform between two bits only. Like for example, if we try to take 0 and 0, 0 1, 1 0 and 1 1, where A and B are inputs, right? So you are going to get basically subtraction number, right? 0 minus 0 is 0, and basically you'll have a borrow, you'll have a bar, right? When you are trying to subtract 0 minus 0 is 0 and borrow not required. When you are trying to perform 0 minus 1, you require to take borrow from the other side, and the subtraction also 1. And 1 minus 0 1, no borrow, no borrow required. And 1 minus 1 is 0, no need of taking any kind of borrow, right? So with this truth table, can we able to construct uh, the circuit diagram for it? Yes, right? So as half adder, right? So basically we are going to have a half subtractor, where you are going to give two inputs A and B, which is going to produce subtraction as an output as well as borrow as output, right? So you can able to do this, right? So you can able to do with respect to k map, right? For subtraction, basically if you try to do this, one is a bar b plus a b bar, which is equal to a xr b. So meaning that in half adder also we are going to get the same. Okay, coming to borrow, how we are going to get? We are going to get the 1 because of a bar b, right? So you can do it through k-maps also. So with this one, can you able to construct the circuit diagram? Yes, right? For example, uh, I am trying to construct it for first subtraction. uh, I am giving the inputs a, and another input is b. B. So when you are going to have it like this, I can able to first make it complement, then I will try to perform AND operation. Similarly, for A I will do, for B I am going to make some kind of complement and I will try to perform AND operation, then I will try to make OR operation over this. This is what A XOR B. So like result is subtraction result you are going to get. Similarly for borrow, you need to take A bar B, right? So here you got A bar now. Now for this we need to add B also. This is what I can call it as borrow, right? The same circuit you can able to represent with the help of XOR representation, right? If I am going to have A and B as inputs, I can directly construct a XOR gate is there. XOR gate is there. Then A bar B means for this I am going to define one complement and B. That's it. This is subtraction and this will be, this is the way half subtractor is going to work. Okay. Similarly, full subtraction is there. Full subtractor. Okay. So means certain times you need to take borrow from the another one, right? So you need to perform the borrow from three variables or three digits. We can say bits, 3 bits. So if you would like to subtract from 3 bits, I can go for full subtractor, right? So means if I am having full subtractor, it can take the inputs A and B, where you are going to have one more input as J. I can call it as a C only, right? Yes. So you are going to get again subtraction. What is the result? And you are going to have, right, the same thing. If you are going to construct with the help of the truth table, ABC as inputs, 110 and triple one, right? This sequence you know, right? So finally my subtraction value, and when I'm trying to do subtraction for the third bit, whether I have to take the borrow or not, right? When you are trying to do it between 2 bits, you can able to directly know, right? So now try to observe. I am trying to perform subtraction over 3 bits, so there is no bar required, and there is no there is 0 is subtraction. And when you are trying to perform a minus b, 0 minus 0 is 0, there is no problem. But 0 minus 1 is you require to take the borrow 1, and its subtraction is 1. Similarly, when 0 1 0 is there, you have to take out borrow from the other side, and you will get 1, right? That 1 you are going to place. So finally you are going to get the 1. From 0 0 1 0 1 1, you are going to get the borrow, because 0 minus 1 is borrow 1, and that 1 minus 1 is 0. 0. From 100, if you are trying to make subtraction, you will get subtraction as 1 and borrow is 0. And this one, 1 minus 0 is 1, 1 minus 1 is 0. There is no need of borrow. 1 minus 1 is 0, 0 minus 0 is 0, so there is no need of borrow. But coming to here, try to observe, 1 minus 1 is 0, there is no problem. But 0 minus 1 is, you have to take the borrow from other side, and its value is 1. Right? Now from this one, if you are going to construct the circuit for this, meaning that we need to first minimize this expression, right? So basically you can do the minimization with help of k maps. A B C, if I take this is 0 1 0 0 0 1 1 1 1 0. Okay, but the value of this 1 2 1 2 4 and 7, 1 2 4 and 7, right? 1 2 4 and 7 and 7, right? So which is as like as, again I said, A should be XOR with B, should be XOR with C, XOR with C. Similarly, if you are trying to construct it for borrow, you are going to have A B C B C. So you are going to get the values 1 2 3 and 7, 1 2 3 and 7, right? 1 2 3 and 7. So you can able to do this one, right? So I can write like in the form of minimization. Actually, if I am going to perform in the form of minimization, uh, it will be A bar B bar C plus A bar B C bar plus A bar B C plus A B C, A B C, right? As like as I am trying to perform in full adder, the same procedure I am trying to follow, because I can able to represent in the form of uh, half subtractor or not. Okay, fine. See, try to do that. Here I can able to take out A bar B from this one. if I am trying to take a bar b, you will get c plus c bar. From these two can I take c as common? You are going to get a bar b bar plus ab. So you are going to get a bar b plus, can I try to take this x nor in terms of XOR? Yes, you can take out a XOR b over NOR operator dot c. Yes, we can do this, right? So basically up to here we can do, and this one you can do with help of basic gates. We can able to construct, there is no problem. Okay, right, now I am trying to do construct for subtraction directly in one circuit. I am trying to have a and b as inputs, I am going to have a subtract a XOR b, we got, right? Now for this one I am going to give one input c, then you are going to get a XOR b XOR c. So you got here subtraction. Now we need to find out borrow. We need to find the borrow, right? Borrow you are going to get, here. Try to observe how can you get, right? So see, uh, this one is a XOR b. For this I am going to make a complement. And this c I am going to perform and operate. Okay, can we able to get now a bar b? Yes, a, which is a bar, and b, right? Yes, so you are going to get here a bar b. So this a bar b, I am going to perform OR operation over a XOR b whole complement dot c. So here I am going to get. So now you got the bar. Okay, this is what full subtractor. Okay, guys, if you are able to clearly observe, right? What is half subtractor? Half subtractor is like XOR gate with not and AND operator. The same, right? It's look like this one. Okay, and also this will be like this one, right? Meaning that you can able to construct one full subtractor with the help of two half subtractors. Okay, let's see binary subtractor. Okay, so when you are trying to perform the subtraction for the binary numbers or in system format, so basically negative numbers you are going to do in the form of either ones complement or in the form of twos complement, right? Twos complement. Like for example, if I am going to have a naught, a1, a2, and a3, b naught, b1, b2, and b3. If you are trying to perform subtraction, then what you are trying to do basically, the actual number is as usual a2 and a3. For example, I am trying to represent in the form of twos complement, assume, right? If I am trying to represent in the form of twos complement, what I am going to do, I am going to basically convert this b0 b1 b2 b3 into twos complement, right? For that what I can do, I can make b0 complement, b1 complement, b2 complement, and b3 complement. For this I am going to add simply plus 1, right? Which means this is 2's complement of the number, meaning that this is actually the negative number of this one, right? Now once you find uh, like two's complement of a number and the actual other number, can you able to directly perform the plus operation so that it is going to get the result? That result will be the binary subtractor. I hope you know how to perform binary subtraction, right? Yes. The same logic here also we can follow, right? Now what I am trying to do now, I am trying to construct the circuit for this. Now if you are able to observe here, at a stretch, at a stretch, am I going to am I going to add three numbers or not? Am I going to add three numbers? So if I would like to add three numbers, can I use full adder here? Yes, I can able to use full adder. So what I can do, I will take four full adders. Take four full adders. Okay, full adders I have taken, right? Now, now actually for this full adder, I am going to give a naught as usual, a naught, a1 is as usual, a2 is as usual, and a3 is as usual. But but b naught should not be given. Instead, you should have to give b naught bar, right? So what I am trying to do now, I am going to give as b naught bar, b1 bar, b2 bar, and b3 bar, right? Meaning that I am trying to represent its complement. For this, what I am going to do, I am going to give plus 1 as input, right? If I am going to give the C naught as 1 now, C naught as 1 now, if you are able to observe this one indirectly acting as this particular part, indirectly acting as A naught, B naught bar, and 1, right? Which is going to produce S naught and produce some carry as C1, right? Yes. That's why I'm trying to convert into 2's complement. It is easy. Now it is going to produce again. Uh, Let me take this as a carry C1, this as a subtraction S0. So you know, right? S1 and S2 and S3, and this will be C2, C2 and C3, and you are going to get C4 carry P. So this is the corresponding circuit for 4-bit binary subtract. 4-bit binary subtractor using full adders. Using full adders, right? Yes. Guys, we are trying to see if you are going to check this circuit, binary subtractor, or if you are able to check the binary adder. Those two circuits are completely same, except these terminologies like B3 as B3 bar, B2 as B2 bar, B1 as B1 bar, B0 as B0 bar, and C0 as in place of 0 it is making as 1. In place of making as 1. Right? Is there any chance to combine the binary adder and binary subtractor in the same circuit? Yes, it is possible, right? So in the same circuit, we can able to perform adder as well as subtractor, right? So here we are trying to work with the 4-bit, so I made it as 4-bit binary adder subtractor, so that we need to use multiple circuits, right? So for subtraction of 4-bit number we should not use one circuit, and for addition of 4-bit number we should not use another circuit. If you are able to construct it in the same circuit, then it is very easy for us to solve, right? Yes. How can you do means, see guys, see, the logic will be like you have to, when you are going to get see, first I will try to take mm, the full adders first. Okay, four full adders I am having. This is, you know, 4 full ladders are there. Okay, for these 4 full ladders, I think there is no change in the initial A naught, right? When it is addition or when it is an subtraction, there is no change in the A values. A values. But try to observe, if we are going to give like addition, if we are going to give addition as requirement, B naught should be as it is as B naught. But when we are going to perform subtraction, B naught should be as B naught complement. B naught should be as B naught complement, right? Yes. So where can I get this kind of requirement, this kind of possibility, right? See, the real world application of XOR gate, the real world application of XOR gate is, if you are going to have an input X, and the another input is 0, and if you are trying to perform XOR operation, what you are going to get now? You are going to get X bar into 0 plus 0 bar into X. 0 bar into X. So finally you are going to get what? This is 0 plus X. So you are going to get X. If you are able to observe, X XOR with 1. So X bar into 1 plus 1 bar into X. So you are going to get X bar plus 0, that is X bar. Guys, with these things you can able to understood, right? When you are going to have an input like B naught, see, observe, when you are going to have an input like B naught, and I am going to have input as 0, another input as 0, what is the output you are going to get? B naught. If you are going to have the input like B naught, another input as 1, what is the output you are going to get? B naught bar. B naught bar, right? Now just think about the situation. Can I use here the inputs as XNOR gate, sorry, XOR gate? If I'm going to use XOR gate, see, try to observe, I'm going to have B naught, and if I'm going to use the XOR gate as usual, which is going to take the B naught as input, and for this input, if I give 1 as input, what is going to happen? If I give 1 as input, this B naught will be act as, see, B naught with 1, you are going to get B naught bar, right? Meaning that if I am going to give B naught with 1, you are going to get B naught bar. So are you going to satisfy B naught bar or not? Yes. So what I will do now, I will try to do all like this. B1, B2, sorry, it should be B2 and it will be B3. Guys, now try to observe. So if I am going to pass this entire input to all these B3, B2, B1 and B0, right? Now observe what might be happening if I am going to pass here 1. Here I am going to get B0 bar. See, I am just making a notation. I am going to get B0 bar. I am going to get B1 bar. I am going to get B2 bar. I am going to get B3 bar. Right? So you can able to observe A0 plus B1 B0 bar. Then you have to add plus 1. Yes, can I give the same input here? Yes. Now this circuit will be acting as subtractor. Okay, fine. If you are able to clearly observe, this same circuit will be acting as adder also. If I pass 0, what is going to happen? If I pass 0, see, I will make it clear for you for understandability. Representation. As I passed 1, it is acting as subtractor. Now if I pass black color as 0, now what is going to happen? 0 will comes here, will comes here. 0 with b naught. 0 with b naught is what? B naught. So b naught will comes here, b1, b2 and b3. Observe now, for addition, a naught and b naught, a1 b1, a2 b2, a3 b3, which is like as usual binary adder, binary adder. So meaning that here, in place of this two data, you can place simply a kind of control input. We can call it as control input. Control input, where this control input simply defines, if you are going to place m as 0, I can call this circuit as adder. When you place m value as 1, I can call it as subtract. I can call it a subtract, right? Now try to complete the remaining diagram, right? So this will be C1, C2 and C3, and if there is any carry, you are going to generate C4, and the outputs will be S naught, S1, S2 and S3, right? So this is the corresponding 4-bit binary adder and subtractor in the same circuit. Yes, ma'am. So this is for today's class.